Good evening, boys and girls. Welcome to another lesson on Technical Sciences Grade 12. It is me again, Mr. Sibanyoni, and we are continuing with organic chemistry. And remember, the section that we are dealing with this time around, it is still on physical properties. And we have really dealt with the topic extensively. So we are doing different types of questions that we are going to use to concretize the knowledge that we have. And that is why on a daily basis, I am choosing for you different types of questions so that you can see the different styles in which these questions can be asked. Like today, we will be looking at physical properties still, but we will be looking at a question that is more of an experimental type of questions where we need to identify variables and so on. And hence, we are still continuing with physical properties. I hope you are ready for me and you will enjoy the lesson. Hopefully you have your pen and paper ready so that you are able to take down notes. Now, let us look at the overview of the lesson for today. Firstly, we will check just for a minute or two what the examination guideline expects us to know in terms of this section on physical properties. And now and again, I'm taking 2 minutes to do that because we have new learners that are joining us on different days, and they need to also know that what is expected of us on this particular section. And in the features of the topic, we will be learning more of these physical properties. We will be making sure that we really put our knowledge together and concepts together on physical properties by definitely answering structured questions on this topic. And lastly, I will be giving you more tips about this particular topic in terms of how you can prepare for an examination so that you are able to ace this section of the work. Right. Now, remember, according to your examination guidelines, we are studying mainly 3 physical properties: the boiling point, the melting point, and the vapor pressure, right, in organic molecules. Yes, there is viscosity there that is indicated, but remember, we have a separate topic for viscosity, and that we deal with it more in paper 1 in technical sciences. And then remember, we must be able to discuss the relationships of these physical properties in relation to the homologous series that we have learned about, especially when we're doing nomenclature. In other words, we must know very well the boiling points, the melting points, and the vapor pressures of different homologous series and actually be able to compare them. And that is why in the second bullet there, it tells us we must be able to compare physical properties of different homologous series. For example, there, that is where I told you, if I gave you an organic molecule like butane, which is an alkane, and I gave you a molecule like butanol, maybe butan 2-ol or butan 1-ol, which is an alcohol, I must be able to compare their boiling points, their melting points, as well as their vapor pressure. That's exactly what that bullet is saying. And then for an example that has been given, we must be able to establish or explain the relationship between physical properties, for example, the boiling point, as well as the intermolecular forces. In terms of strength, I must be able to explain the relationship between boiling point and the type of intermolecular forces that I'm getting in a molecule. I must be able, again, to explain the relationship between boiling point and the chain length, which we also refer to as the surface area. I must also be able to talk about boiling point as well in relation to what happens when I branch a chain. So this is still to do with chain length, because you will remember when you start to branch a chain, you are actually shortening the parent chain, and hence the surface area decreases. So we've really talked about this, and I'm not really trying to teach you now. I'm just reminding you, and hence we are just going a little bit quicker. And then I told you, when you go to your examination guidelines, you will see that some of these definitions are omitted, which is the definition of the boiling point, the melting point, and the vapor pressure. And I told you that you need to know them, regardless of whether you see them in the examination guidelines and so on. And hence, I gave you time to actually take note of these particular definitions. So we must be able to talk about that. Then we further engaged on physical properties, where we actually looked at the relationship between vapor pressure and boiling point. And just as a reminder, you know that an organic molecule that has a high boiling point will have a low vapor pressure. Again, my dear learners, you know the opposite is true. If a molecule has a low boiling point, then its vapor pressure will be high. So when we are comparing different organic molecules, let's say organic molecule A and B, if I see that A has a higher boiling point than B, then automatically I know that A will have a lower vapor pressure than B. So those are basic things that you must be able to pick up when you get a question. Then we talked about the relationship again between physical properties and intermolecular forces. And we said the stronger the intermolecular forces are, the higher the boiling point is going to be, the higher the melting point is going to be, but the lower the vapor pressure is going to be. In other words, if I see that a molecule has a higher boiling point, automatically it must tell me that the melting point is also going to be high. But it must also tell me that the vapor pressure is going to be low. When I realize that a molecule has a low boiling point, then it must tell me that the melting point is also going to be lower, but it must tell me that the vapor pressure is going to be high. And again, we know stronger intermolecular forces will result in a boiling point that is high, a melting point that is high, but a vapor pressure that is low. And weaker intermolecular forces will result in a boiling point that is low, a melting point that is low, but a vapor pressure that is high. And then we went further to learn about the types of intermolecular forces. And I said we are going to learn about three. We learned about London forces, we learned about dipole-dipole forces, and we learned about hydrogen bonds. And we took note that of these three types of intermolecular forces, London forces are the weakest of intermolecular forces. In other words, they are not as strong. And the hydrogen bonds, they are the strongest of these three. And then we are left with dipole-dipole forces. And the dipole-dipole forces, we say they have medium strength. In other words, the dipole-dipole forces are actually stronger than the London forces, but they are weaker than the hydrogen bonds. And then we agreed further when we talked about London forces. We said the London forces, we get them on a hydrocarbon chain. And that is why our hydrocarbons are in the homologous series alkanes, alkenes, and alkynes. And therefore, the London forces, we get them in those three homologous series, those that are made up of only a hydrocarbon chain. And then we said for our syllabus, the hydrogen bonds, we will only get them in alcohols and carboxylic acids. Now, when we get our hydrogen bonds in alcohols and carboxylic acids, then by knowing all of that, we can then determine where we get the dipole-dipole forces. And the dipole-dipole forces, we will get them in the remaining homologous series. Remember what I said to you, London forces, alkanes, alkenes, alkynes. Hydrogen bonds, alcohols, carboxylic acids. So all the other homologous series that I did not mention right now, which are your haloalkanes, which are your aldehydes, your ketones, your esters, and so on, you will get dipole-dipole forces. And I went on to talk about these hydrogen bonds. And I told you that the hydrogen bonds in carboxylic acids are actually stronger than the hydrogen bonds in your alcohols. And you must know why carboxylic acids have stronger hydrogen bonds than alcohols. And we note that carboxylic acids, they actually have stronger hydrogen bonds because they have two sides for hydrogen bonding. But alcohols, they only have one side for hydrogen bonding. And that is why the hydrogen bonds in carboxylic acids are actually more because it has two sides for hydrogen bonding. So it forms more hydrogen bonds and hence they are stronger. But your alcohols will form less hydrogen bonds and hence they are not as strong as those of carboxylic acids. But take heed of this. It does not mean the hydrogen bonds of alcohols are weak. They are still strong. It's just that they are not as strong as those of carboxylic acids. In other words, if I gave you a molecule like pentanol and pentanoic acid, I would then know that pentanol is an alcohol with hydrogen bonds. Pentanoic acid is a carboxylic acid with hydrogen bonds. I am not expecting them to have the same boiling point. Why? Because pentanoic acid, its hydrogen bonds will be stronger than the hydrogen bonds of pentanol. Why? Because pentanoic acid is a carboxylic acid and it has two sides for hydrogen bonding. And pentanol, it's an alcohol and it has one side for hydrogen bonding. So the boiling points are also going to be different. And I expect the boiling point of the carboxylic acid, which is the pentanoic acid, to be higher than the boiling point of the alcohol, which is pentanol, even though they both have 5 carbons in the parent chain. So be aware of that. And it is also critical for you to know, when you explain these type of questions, you must be able to also know exactly the intermolecular forces that are present in these molecules altogether. Again, my dear learners, when we deal with alcohols and carboxylic acids, there tends to be a confusion because learners always assume that they both have hydrogen bonds and therefore the boiling point must be the same. It is very clear, if the boiling point is not the same, it means the strength of the intermolecular forces is not the same. So the one with the higher boiling point will be the one with stronger intermolecular forces, and the one with the lowest boiling point will be the one with the weakest intermolecular forces. And this is a comparison. We compare it to the other one. And remember, I'm simply talking about boiling point. You must know that automatically, if the boiling point is high, the melting point is high, but the vapor pressure is low. And the opposite is also true. So don't always think that we will be giving you questions in terms of boiling point only. We could be giving you in terms of vapor pressure, and we could be giving you in terms of the melting point. So remember all of that. So this is just a quick summary so that we refresh our memory and then we are able to move to questions. Now, I know some of you, you read a lot and you actually are aware that, for example, in an aldehyde, for example, butanol, there's actually dipole-dipole forces. And I know some of you are well aware that there is also London forces. Why? Because butanol still has that hydrocarbon part of the chain. So the hydrocarbon part of the chain has the London forces. But the functional group, which is the formal group, that one on the first carbon, is polar in nature. And hence we have dipole-dipole forces. So that functional group is actually the one that is giving us the dipole-dipole forces. But the hydrocarbon part of that molecule is actually giving us London forces. And I said to you, do not be confused. We are only going to deal with the significant intermolecular forces that are causing the boiling point to be different. And that is why we must stick to alkanes, alkenes, alkynes having London forces. We must stick to alcohols and carboxylic acids having hydrogen bonds. And your aldehydes, your esters, your haloalkanes, your ketones, we stick to those having dipole-dipole forces. Let us avoid that particular confusion altogether. We don't really want to change the signs, but we also just want you to be able to collect all the marks that you need. And sticking to that is definitely going to assist you. So here we are given a question. It reads as follows. During a practical investigation, the boiling points of the first 6 straight chain alkanes were determined, and the results were recorded in the table below. Now, I can tell you, my dear learners, from just reading that once, there isn't much that I have grasped. So you go back and you read it. So, or you interpret it. So what we can establish here, during a practical investigation, the boiling points of the first 6 straight chain alkanes, it means they are determining the boiling point and they are only focusing on the first 6 alkanes, and those alkanes must be straight chains. Automatically tells me that they are dealing with methane, ethane, propane, butane, pentane, and hexane, because they are straight chains, no substituents. And the boiling points were determined. So these people were actually trying to find out what their boiling points are. They were determining the boiling points. And the results were recorded in the table below. So if you look at our table, they show us the alkanes. It's our methane all the way up to hexane. And then we've been given the molecular formula of each of those molecules. So we have the molecular formula of methane all the way to the molecular formula of hexane. Remember, my dear learners, and we are not doing nomenclature actually now, but when we talk about molecular formula, remember, it's actually not a structure. A structure gives you the structural formula. So you will be showing us the atom and which atom is bonded to which. But in a molecular formula, remember what you do is you tell us how many of each type of atom are present in that molecule. For example, in methane, one type of atom is carbon, so we have one of those. One other type of atom is hydrogen, so we have 4 of those. And we are given the boiling points, and one boiling point there is measured in degrees Celsius. So this is negative 164 degrees Celsius, all the way up to hexane with 69 degrees Celsius. Before we even go further, let us try and identify which molecule here has the lowest boiling point. So I see methane with minus 164 degrees Celsius. I see hexane with 69 degrees Celsius. Remember, my dear learners, mathematically, any number that is negative and bigger, it's actually a small number. So if I see negative 164, I know that that is a very small value. But when I see a positive 69, I know that it is a very large value altogether, or not necessarily very large, but it is actually larger than negative 164. Why is 69 larger than negative 164? It's because the 69 is positive and the 164 is negative. So methane with a boiling point of minus 164 degrees Celsius, it's actually a lower boiling point. And 69 degrees Celsius, it's a higher boiling point. Again, let's compare methane and ethane. Methane has a boiling point of minus 164 degrees Celsius, and ethane has a boiling point of minus 89 degrees Celsius. So let us try and understand that. Now, when we look at this one, we can see minus 164. It's actually a smaller number compared to minus 89 altogether, because minus 164 is actually far from 0, or it is far from being positive, and that is why it is a smaller value. Minus 89, when you compare it to minus 164, we can see that minus 89 is not far from 0, or minus 89 is not far from being positive. So it is a larger value when you compare it to minus 164. And I am emphasizing this because some of the learners, when they see 164, they just think that 164 is the largest number there, but they don't take note that the 164 is negative. So it's far from being positive compared to all these numbers. And as a result, it's a smaller boiling point. Right. Now, what is the trend in the boiling point that I can see here? And this is a question that we can ask you, and it's not really being asked here. But when we ask you for the trend in the boiling point, we are asking you for the pattern. What do you observe here in terms of boiling point? That is what the term trend means. And you must be familiar with that because you will get it also at the end of the year. So when you talk about the pattern, the trend, we are talking about the pattern. What do you observe here in terms of boiling point? And I can see that boiling point increases from methane to hexane altogether. And we could be asked to explain that particular trend. We could be asked to explain why the boiling point increases from methane to hexane. Right, so we take note of that. What else can we see here? My dear learners, this alkane, they are all straight chains. This one is a meth. So this one only has one carbon in the parent chain. In the longest chain of carbons without breaking, we actually have one. Eth, it's 2. Prop, it's 3. But, it's 4. Pent, it's 5. Hex, it's 6. So what does that tell me when I go from methane to hexane? It tells me that the parent chain is increasing in its length. So the chain length of the parent is increasing from methane all the way up to hexane. In other words, from methane going to hexane, the surface area is increasing. Why? Because the longest chain of carbons without breaking, which is the parent chain, is increasing. And we can then see the relationship here that, oh, when the chain length is increasing, I can then check that the boiling point is also increasing. And this is what you can establish from this table before you even go to the questions that, oh, so when the surface area is increasing or when the chain length is increasing, the boiling point is also increasing. So we take note of that. Now we go to the questions. 14.1. Write down the most important use of the alkanes in the above table. Now, my dear learners, we know that alkanes are used as fuels altogether. Your petrol is a mixture of different alkanes. The gas that you use at home, it's usually made of propane. In your gas stoves and so on, that's a form of fuel because it will give you heat. Those, I know you don't smoke, but in your cigarette lighters, not in your cigarette lighters. In cigarette lighters, then that is also a mixture of hydrocarbons. So they are used as fuels, and we talked about this when we did organic reactions. Then we are asked for the general formula of the alkanes. Now, when you look at this question has nothing to do with physical properties actually. It has everything to do with nomenclature, but we integrate questions. So the general formula of alkanes, we know it's a recall question. It's CnH2n plus 2. And you will remember the N represents the number of carbon atoms. And I told you again, my dear learners, that if you are unable to recall the general formula from your head, you can actually work it out altogether. For example, let us look at one of these. We have C6H14. So we know that, okay, this general formula must have carbons. This general formula must have hydrogens. Then we check, oh, if the number of carbons is n, then I will just put n there. So if I have 6 hydrogens and I have 14 hydrogens, I can actually say the number of hydrogens is 2 times the number of carbon atoms, which would then be 12 plus another 2. And therefore, it must be 2n plus 2. So a general formula, you can always work it out. So we get Cn H2n plus 2. Then the next question says, for this investigation, write down the following: the dependent variable and the independent variable. Now, let us start with the independent variable. And I want to put it simple to you, and that's not a definition of an independent variable, but it will help you to remember easily. An independent variable is the variable that you are changing during the experiment. So anything that is changing during the experiment is an independent variable. Now, when I say anything that is changing, we are actually saying anything that you are changing personally, the person that is experimenting. So the person that is experimenting here started using methane, then used ethane, then used propane, then used butane, then pentane and hexane. So what is changing here, I can see that it is the chain length of the hydrocarbon. What I can see is that the molecule that we are using over and one after the other is actually longer than the previous one. So the length of the parent chain is increasing. So our answer there for the independent variable, we are going to say it is the chain length. Another learner could have said it is the surface area. So the variable that the experiment or the experimenter is changing, that is what we call your independent variable. Then we get to the dependent variable. The dependent variable, actually, it's called dependent. Why? Because it depends on something. And what does it depend on? We say it depends on the independent variable. So know this. The dependent variable depends on the independent variable. I will repeat it for you. The dependent variable depends on the independent variable. We go back to our table. What depends? Which variable here depends on the independent variable? So what depends on the chain length? And we say the boiling point depends on the length of the chain. And I can see that when the chain is shorter, the boiling point is low. When the chain length increases, the boiling point increases. When the chain length increases, the boiling point increases. When the chain length increases, the boiling point increases. And we go on and we go on. So I can see that when the chain length is increasing, the boiling point is also increasing. So can you see that the boiling point depends on the chain length? Are we together? Right. So the chain length is our, the boiling point is our dependent variable. Then what conclusion can be drawn from the above results? So we are going to look for the conclusion. Now, when we conclude based on the results. Now, let us look at the results here. The results here are actually based on the independent variable as well as the dependent variable altogether. So we agreed that the dependent variable here, or rather we agreed that the independent variable is the chain length. And we agreed that the dependent variable is the boiling point. So when we make our conclusion, remember for full marks, you must mention the independent variable, you must mention the dependent variable, and give the relationship between that independent variable, dependent variable, and so on, right? So you need to give the relationship between that independent variable as well as the dependent variable altogether. Now, what is the relationship here between the independent variable, which is the chain length, and the dependent variable, which is the boiling point? I can see that an increase in chain length results in an increase in the boiling point. Or simply put, the longer the chain length, the higher the boiling point. So our answer there is the longer the chain length, the higher the boiling point. And then we are asked to write down the name of an alkane that is a liquid at 25 degrees Celsius. Now, a liquid that is, rather, an alkane that is a liquid at 25 degrees Celsius means it must be the organic molecule that has not yet boiled. Now, when I look at methane all the way up to butane, when the temperature is 25 degrees Celsius, we can definitely say they have already boiled. Why can we say they've already boiled? Because methane boiled at -164, ethane boiled at -89, propane boiled at -42, butane boiled at -0.5. So by the time the temperature is 25 degrees Celsius, then they have already boiled. In other words, they are already in a gaseous phase, so they are already gases. Then we are done with those. Let us look at pentane and hexane. Pentane will only start boiling at 36 degrees Celsius. In other words, when the temperature is 25 degrees Celsius, pentane has not yet boiled because it's still waiting for the temperature to actually be 36 degrees Celsius. So at 25 degrees Celsius, it hasn't boiled yet. So if it hasn't boiled, then we know that it will be a liquid. And the same actually applies to hexane because it boils at 25 degrees Celsius altogether. So that is very important because now, rather, it boils at 69 degrees Celsius. So when the temperature is 25 degrees Celsius, it hasn't boiled as yet. So it means it is still in the liquid state because By boiling at 69 means you only start entering the gaseous state when the temperature is 69 degrees Celsius. Anything lower than that, you haven't boiled yet, so the temperature is, rather the state is still your liquid state. Right. So I hope that you understand this one. Quickly to revert to 14.2.3, remember what I said to you. When you conclude, it's usually 3 marks. You mention the 2 variables altogether. So we agreed that the independent variable is the chain length, the dependent variable is the boiling point. So by simply, and I hope it's a safe statement to say, by simply mentioning the variables, you will have 2 marks. By simply saying something about chain length and boiling point, and when you then give the relationship, you will get the 3rd mark altogether. Because that's what we conclude on. We conclude on results, and those results are based on the variables. Then for 14.4, we are told alkanes burn, okay, sorry about that. For 14.3, we actually have 2 of the answers, and that is pentane and hexane, but they only wanted 1, so any of the 2 it's actually correct. Altogether, right? Maybe I should write down 14.2.3 for you. We said the conclusion here is that the longer the chain length, or one of you could have said an increase in chain length, the longer the chain length or the larger the surface area, still the same thing, the longer the chain length, the higher the boiling point. Telling you this statement could easily be 2 or 3 marks. So I'll just give it 2 marks here for the fact that you mentioned the variables and then you gave the relationship between those. So we go to 14.4. Alkanes burn readily in oxygen. Write down a balanced equation using molecular formulae for the combustion of propane in oxygen, in excess oxygen. Right, you will remember what this means. When we say an alkane is undergoing combustion, definitely it burns in the presence of oxygen gas. And it is a favor there for them to actually tell you in excess oxygen, because you must already associate combustion with oxygen gas. And we are having propane burning in excess oxygen. So we must write down a balanced equation. So it has to be balanced. And we must use molecular formulae. Remember what molecular formulae are. And we've been given them. They show how many of each type of atom are present in that molecule. And propane, we see the molecular formula, it's C3H8. Right, and we are very lucky that we've been given the molecular formula there. Otherwise, you need to work it out. And I hope you can do that by now. C3H8 plus O2. This is the first mark because it's the mark of the reactants. Now, some of you, my dear learners, you will just leave it like that and you don't show us even an arrow. Remember, if you don't show us an arrow, then this is not an equation. It's not a chemical reaction. So you wouldn't even get that mark there. So we must have an arrow. At least if we have an arrow, if you leave everything out, we can definitely see that, oh, C3H8 as well as O2, they are on the left-hand side, and therefore they are reactants. And then my product, remember, it will always be carbon dioxide and water. So it will always be CO2 and H2O. Then we will get another mark for the products. Good. Then we must balance. Remember what I said to you? Make it easy for yourself. Start with the number of carbons then the number of hydrogens, and then the number of oxygens. Do it in that particular order. Then we check how many carbons on the left? 3. How many carbons on the right? 1. So where am I short? On the right hand side. And how am I going to balance? I'm going to balance there with the 3. Then 3 carbons on the left, 3 carbons on the right. Then I check my hydrogens. How many on the left? 8. How many on the right? 2. So I owe on the right hand side. So I must balance on the right hand side. So to make this an 8, I see there's already a 2 on the hydrogen, so I must balance there with a 4, because 4 multiplied by 2 will give me 8. Then I look at the oxygen atoms. On the left, I have 2. On the right, I have 3, and I will multiply by 2, it will give me 6. Again, I have 4, I will multiply there by that invisible 1 on the oxygen. So 4 times 1 gives me 4. So 6 plus 4 will give me 10. So I have 10 oxygen atoms on the right, and on the left I have 2, so it means I owe on the left. And to make this a 10, because I already have a 2 there, I'm going to balance with a 5. Then the last mark is going to be for balancing. This question is always out of 3 marks. The last question, my dear ones, it says, will the boiling point of structural isomers of hexane be higher than, lower than, or equal to that of hexane? Now that is the first part of the question. Then the second part, it says refer to molecular structure, intermolecular forces, and energy needed to explain the answer. Now, my dear learners, the first part, it wants to know if you take the structural isomer of hexane, how will its boiling point be compared to that of hexane? So it means we are dealing with an isomer of hexane as well as hexane. So we must ask ourselves, this isomer, how will its boiling point be? Is the isomer, is the boiling point of the isomer going to be higher than that of hexane? Or the boiling point of the isomer be lower than that of hexane? Or the boiling point of the isomer be equal to that of hexane? And I know it's a bit tricky, especially in terms of the English, because now you know how the question is phrased, but it is correctly phrased. You just need to interpret it correctly. It wants to know, will the boiling point of the structural isomers of that hexane be higher than or lower than? So you must tell them with reference to the structural isomer how the boiling point of the isomer is going to be, not how the boiling point of the hexane is going to be altogether. Now, you can't answer this question when you don't even know the isomer of hexane. And there are quite a number of isomers. I'll just draw one. Now, it is a hydrocarbon. If it is a hydrocarbon, it means it's carbons and hydrogens only. So there is no way that you can actually move a hydrogen from one point to another. So you can't make it a positional isomer. And you also can't change functional groups because everything is single bonds between carbon and carbon atoms, and the atoms are the same. So you can't have functional isomers. So automatically you know that it must be functional isomers. To make it a just a point of correction quickly, it must be chain isomers altogether. And how do I make a chain isomer of hexane? Obviously now, I have to shorten the chain. For example, I make it now 5 carbons long, and the 6th carbon becomes a branch. So this is going to be the isomer altogether. And there's quite a number of these isomers. But the fact of the matter is, all the isomers of hexane are going to be branched like this one. This isomer is branched. And remember, Why is this an isomer? Because it has, you see, the molecular formula of hexane is C6H14. And even if you look at this molecule, it will be C6H14. 1, 2, 3, 4, 5, 6 carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 hydrogens. So they are organic molecules with the same molecular formula but different structural formula. And they are definitely chain isomers because they are organic molecules with the same molecular formula but a different type of chain. Why different type of chain? Because this one, this is actually 2-methyl pentane. 2-methyl pentane. 2-methyl pentane is a branched chain. It has a branch. There we have a substituent. But when we look at hexane, hexane is a straight chain. So what do we say then? We then say, because this one, the longest chain without breaking, it's now a pent. It's 5 carbons long. But with hexane, it's 6 carbons long. It means the chain length of hexane is larger than the chain length of pentane. So the surface area of hexane is larger than the surface area of 2-methyl pentane. And we know the longer the chain length, the stronger the intermolecular forces. The shorter the chain length, the weaker the intermolecular forces. And hexane will have a longer chain length, so it will have a high boiling point. 2-methyl pentane has a shorter chain length because it is branched, so it will have a low boiling point. In other words, this isomer will have a boiling point that is lower than that of hexane. Are we together? Now we must explain. Remember, I taught you, and I will just write this in purple. This is for question 14.5. I said we will use 3 headings. Remember, here it's a favor for them to tell you what to refer to. The first heading we agreed, we'll talk about the course. And I said to you, with the course, you check, am I comparing molecules from the same homologous series? And yes, 2-methyl pentane and hexane, they are both alkanes. In other words, then the course has to be the chain length. Then I will say hexane has a longer chain length than its isomers. Yes. Because there's actually more than one isomer. I just drew one for you. Hexane has a longer chain length than its isomers. So I'm not just saying it has a longer chain length. You have to explain thoroughly that it has a longer chain length than its isomers. If you omit that, my dear learners, we can't give you a mark because remember here, you are doing a comparison. So you have to show that it is something between hexane and its isomers. So it must be very clear. Then the second heading you will remember, we talk about the strength of intermolecular forces. And I told you that you are not going to write IMF, you will write in full intermolecular forces. I just don't have enough space here. So because we've already established that hexane will have a higher boiling point because it has a larger surface area, it means its intermolecular forces are strong compared to that of the isomer. Or those of the isomer are weaker because the chain length is smaller, so the intermolecular forces will be less, and that is why the boiling point will be lower. So I will say the intermolecular forces of hexane are stronger than the intermolecular forces of hexane are stronger than those of its isomers. Good. That will carry another mark. And lastly, I must talk about the energy. Now, if hexane has stronger intermolecular forces, it means we will need more energy to break those intermolecular forces or to overcome those intermolecular forces. And the isomers, if the intermolecular forces are weaker, then we will need less energy to break those intermolecular forces. So there we'll say more energy is needed to break intermolecular forces of hexane than its isomers. And that will be your final mark all together. And we write it in point form. We've really discussed this extensively. So if you check them, my dear learners, actually these headings here are those headings that they actually talked about. You see that they said refer to molecular structure. When you talk about the course there, can you see that course says hexane has a longer chain length than its isomers? It means the structure there is actually different. In terms of molecular structure, the other one is a longer chain and the other, its isomers are shorter chains. And that will give you all your marks. So really, my dear learners, you need to prepare, interpret your tables. Do not just rush to the questions. Look out for the patterns. Identify the variables that are there. Make conclusions there for yourselves. And when you are done doing that, then you can go and look at the questions. So these are also experimental type or investigation type of questions that you can expect at the end of your during your final examination at the end of the year. So thank you very much. I hope you have enjoyed the lesson. I certainly did, and I will see you tomorrow, same time, same place. Enjoy the rest of the evening. Goodbye.